Hello, everyone, and welcome to our series of podcasts on HPCC systems. Today, we have Richard to talk again on our migration and journey to the cloud. He's going to cover a little bit of what he covered at the very beginning of this series, but also include some additional overview on our current strategy and what has been our current developments as well. A lot of things have happened over several weeks in the last couple of months, and Richard can really give us a good amount of perspective on those things and more. Hello, Richard, and welcome.
Hello.
Thank you for being here. Hey, Richard, tell us a little bit about what we have been doing on HPCC over the last several weeks. We've been quite active. We released quite a few minor enhancements in versions, but we also released a newer version, and we are working actively on the next one, right?
Yes, we released 7.8 was the first version that had any cloud support. We released 7.10 3 months after that, and we released. We're now working on 7.12, which is due for the start of October. Each of them has a bit more support for the cloud. It's a bit more robust. By the time we get to 7.12, we're hoping it'll be mostly cooked. There may still be the odd hole here and there, but we should at least know what things are going to look like, even if we haven't completely finished implementing them.
Very good. So, seen from the outside, it seems that we first focus on the compute capabilities of 4. Then we started to look at the storage piece, and then we are going towards Roxy and the other components. Is that the way the progress has been made, or do you think there is more interleaving across that?
Kind of. It is a bit interleaved, though. We have a lot more to do on the storage capabilities. Our first release was fairly basic in terms of what you could do with storage. You could, if you could describe where you wanted to store your data as a persistent volume, then you could store your data there. But we're moving towards giving you much more options for storing data. For example, if you want to store it in Azure blobs or S3 containers or data lakes or any of the other possible locations, and you'll be able to configure that potentially even on a file by file or at least scope by scope basis, so that some data files you can access on that don't need rapid access, that you're accessing less frequently, you'll put into cheaper but slower storage, whereas things that need access very, very rapidly or accessed all the time, you can put into more expensive but faster storage.
So traditionally, we always supported any storage that was POSIX compliant, but it seems to me that now we are expanding that to also support HTTPS type access to storage, or HTTP access to storage as well, or API based?
Certainly API based access to storage for things like the blobs. They tend to be accessed using SOAP calls or similar. We have actually always had the ability to plug in access to, if you could write code to access something as if it was a file, then you could access it from Thor. For example, we've had the ability to access Git repositories, which is done via an API, or files inside zip files, which again is done via an API. And indeed, accessing files that are not on the local machine, which we do via the file serve, that's done via the same hooking mechanism. So we've had the hooking mechanism in there for many years. It's a question of writing the implementations of those hooks for the specific target file systems.
That is very cool. But some of these file systems that we are talking about, or file access strategies, have different type of performance characteristics. Some of them allow for random access. Some others require sequential access. So how do we ensure that we have the right file system there, or how do we hint the user to use the correct one?
Well, there will be some rules here and there that we'll have to say you can't use a file system that only supports sequential reads if you're wanting to read it randomly. But most of the time, most of our file accesses are in fact sequential. Certainly in Thor, if you're not using an index, it's going to be read sequentially. When writing files, we generally write them sequentially. We have had to make some changes, for example, in the index writing code, so that we've made some changes so that we can write an index only ever writing sequentially. There were 2 or 3 places in the old index writing code that would seek back to the beginning to update a few things, and we've made some changes to the layout of the file so that we don't have to do that anymore. So it is now possible to write an index completely sequentially. We've had to make some changes to things like, for example, in a standard local POSIX file system, there are some operations which are very cheap. Finding out the size of a file is very cheap. In some of these APIs, that counts as a call that you get charged, however many cents for an access is. So you don't want to do it any more than you have to. So we've had to start thinking about ways of restructuring the code slightly to avoid unnecessary access in order to avoid unnecessary cost. But for the most part, most of these remote files or API accessed files will be okay for most purposes. The trade-offs will be which one's going to give you the performance you want and which one's going to give you the cost you want.
Yeah, we had a few discussions with other people as well on this and how this is a fairly complex optimization problem. You need to define what you want to optimize for, and sometimes you have trade-offs. You might optimize for something more, but then you lose on the other side.
Well, optimization is always a series of trade-offs. But yes, I mean, one of the things that we will be optimizing for in the first versions is speed to market. We'll make sure it works first, and then we'll worry about, okay, can we shave a few cents here and there off the file accesses? Can we shave a few seconds or minutes or hours or whatever off the speed?
Very good, but certainly giving people the option to select different things and to optimize themselves for some things is useful. And more if we can give them some visibility into this. I know that there is some work going into ECL Watch to build capabilities to try to predict, based on historic execution of certain work units, try to predict the codes. And that's going to be quite useful.
Yeah, the work unit analyzer will become quite important in working out, after you run your job, where the time went, where the money went, and where you may want to change things to improve it.
Yeah, sometimes a one-off job, well, it might take a little bit longer or cost you a little bit more money, but it's not that big of a deal. But it's something that runs recurrently every day or every hour.
If it's a one-off job, your biggest cost usually is the developer time. So worrying about making the job run 10 minutes faster by having a developer spend 2 more hours staring at the code isn't a good trade-off. But,
very good point. Very good point. So, okay, so let me touch on a more complex or maybe for future facing problem. So this I assume that applies to everything, but of course certainly applies perhaps more to Thor. But how about Roxy? What's in the Roxy front? What's been done so far? What's been planned?
Roxy is a more complex problem in some ways, well, in many ways. What's that? What a conference call. Yeah, Roxy is a more complex problem in many ways. For a start, the data access needs to be fast. It's seeking all over the place. It gets a lot of its performance from things being local. You probably aren't going to want to run Roxy with the files stored on AWS Glacier storage, for example. And probably, in fact, you may find you want to actually move the files into local SSDs as Roxy starts up, or you may find networked SSDs may be fast enough. I mean, there's a lot of unknowns about what's going to be fast enough for Roxy. In the past, in Roxy, on sort of bare metal, we've tended to say, we've got this Roxy, it's big enough to hold all the data. Now let's use it for as many queries as we can use it for, and until it runs out of capacity, and then we bring up another one in parallel. If you're not storing your data on your Roxy, if you're storing your data off node, as is typically going to be the way on the cloud, then that picture changes. What you probably want to do is have all of your data stored on the cloud, on off-node storage, shared between as many compute Roxys as you want. And those compute Roxys, their size isn't going to be governed anymore by what the data size is. It's going to be governed by what the compute load is going to be. And there's no need to share that Roxy between multiple unrelated sets of queries just because they happen to use similar data. So you're probably going to want to start running multiple smaller Roxys in terms of compute size that will cache data that is relevant just for the queries that they're running, that do a small family of queries. So it's going to change the sort of usage picture a little bit, I suspect.
I also want to ask, because sometimes you have different queries that may use similar data, and perhaps one query helps cache data for the other query. So the fact that you're running them sometimes...
If they're using the same files, it doesn't necessarily mean they're using the same parts of those files. I mean, if you've got the header file or a list of dead people that you're looking up to decide whether to send them mailing card or mail-in votes or something, then that's not going to be the same parts of the file necessarily as your file that's doing a mailing list trying to decide, I don't know, who to sell a greenhouse to. Not that we do either of those things.
Good point, good point.
Yeah. The locality of reference is not just at the file level, it's at the sort of area within the file. So I don't know whether they necessarily would share cache. I mean, yes, they'll share a bit, but not necessarily as much as you think.
Do you think there will be some work on improving some of these clever data structures that allow you to hold some sort of very dense cache, like Bloom filters, or like bitmap indices, anything that where you can hold a lot of dense information in one place that you can cache, and then the file might be a large file that is harder to cache?
Yeah, our indexes have supported Bloom filters, and in fact use Bloom filters by default since version 7, I think. So those will help. They're likely to help more in a situation where you can't rely on locality of caching so much. The other thing we're looking at is if you're wanting a Roxy to auto-scale according to load, which we've got all the code in to do, it's no good if the Roxy node that you put in to help has an empty cache and is therefore running slower than other nodes. So automatic cache warming is quite a hot topic, if you like. Now we have all the information we need about what the buddy nodes consider to be the hot part of the cache are. We've cached the unpacked node indexes. We can also store information about what's recently been evicted from that cache, but is probably still in the operating system level cache. So if we use that information to automatically pre-warm the cache when a new node comes up, and only bring it into the list of active nodes once the cache is warm, then the auto-scaling will be a lot more effective, we think. This is something we're experimenting with it at the moment, but I expect it to be quite a significantly useful feature, not just in cloud. In fact, for bare metal, it'll be quite handy.
Yeah, certainly. But ensure that even if you need to auto scale in bare metal,
Yeah, and at the moment,
or expand your rocks, change. Yeah.
Auto scaling in bare metal is done at the cluster level, typically, at least how we do it in house. But those clusters cannot be put online in production until we've warmed them up a bit by sending them. What we do is we send them a few pre-recorded queries. But if we can do better than that by saying, we know what's hot at the moment, not just what's typically hot every day. We know what's hot right now. Let's pre-warm it automatically.
Yeah, that is very interesting. I think it's going to be a new way to give flexibility to Roxy, regardless of which environment they run. You're absolutely right. Before, you brought a new Roxy up and you need to pre-warm it in some way, even with historic things from previous days. But that doesn't give you the best warming strategy. If you knew what's happening in the last hour, that might be far more useful.
Yeah, it's like if you're implementing a Twitter-like thing, then what's hot today is very different to what was hot yesterday. But
yes, absolutely, yeah. So, and tell me about the future. So Roxy, ESP, DALI. So, what's coming down the road? What is the effort now certainly for the next version, the 7.12, or even for the one beyond that, right?
Well, the big effort for 7.12 is finishing off the way of describing lots of different storage locations, making sure that we have tested and described how Roxy works. We've had a big debate about how to deploy queries to Roxy, because is that going against the zero-touch philosophy on the cloud, bringing up a Roxy and then deploying queries to it?
Good point.
Bringing up a Roxy and then deploying new data to it. There's been debates around that. I think the conclusion is probably that we end up doing things more or less the way that we do today.
Well, databases and data storage in the cloud doesn't really fit the zero-touch model all the time.
If you think of deploying new data to Roxy as being like adding data to a database, you can't have a zero-touch database. But adding new queries is a little bit different, and it may well be that, at least from a operational point of view, we will treat that as a zero-touch type operation. We won't expect people to deploy new queries to a Roxy that is live. But whether we'll actually physically prevent it, I'm not sure.
But that makes sense. That might even add an additional layer of robustness or better testing when you deploy a query on that. Yeah. I think it sounds like a good idea if it's not a lot of overhead. But since most times in the cloud you deploy infrastructure as code and Roxy is no different, maybe the overhead is not that much.
I would expect people to organize their Roxy in the cloud such that if they wanted to deploy a whole new set of queries, that they would bring up a new Roxy with a whole new set of queries on, rather than saying, where's my Roxy that I can deploy these queries to, which is what people tend to do now in the bare metal case. So it's as much a mindset thing as anything else.
Yeah, it is, yeah. But I think it might help also in even bare metal environments. It might make deployments of new queries more resilient and less prone to having issues.
Yeah, certainly in cases like the Fusion Roxy, then being able to do green testing or whatever by bringing up your new system alongside your old and makes a lot of sense.
Very good. Okay, Richard, this was great. I thought we got a lot of content, and this is going to help at least paint a picture of where we are going. So tell me, just for kicks, so and for 8.0, what do we expect? So by then people will have a production-ready system that will be cloud-friendly. That's the ultimate goal.
Yes. I hope we're still just about on target to have everything completely production ready in ATO, or maybe what will happen is, maybe we'll need another round of the 7 series, 714 or something. But yes, when we are fully production ready, I guess is when we'll call it ATO. One thing we're working on to make it more production ready rather than more development ready is security side of things. So ingress egress controls at the pod level, so no node can talk to any node that it's not supposed to. Potentially encryption in transit between nodes for systems that require it, that are paranoid about other co-located systems snooping on their data, for example. Secrets management is all got to be worked out, that sort of thing. And all of these things you can ignore in a development environment if you want. They don't stop it working, but they do stop people wanting to or being able to use it in a production environment.
Well, and in a bare metal environment where you can put a big wall, thick wall around it, it is less critical. But certainly here in the cloud, where your things intermingle with something else, someone else's things, then it's a little bit more.
One thing we haven't been able to do on bare metal in the past and can now do in the cloud is define. I mean, we've been able to do it in bare metal, but it's been a separate task. Operations have had to set up their IP tables to control what node can talk to what. Now we can actually define all of those rules from the structure, directly from the Helm chart, because we know, what pod is supposed to talk to what. We define the network services or network policies, I should say, as part of the Helm file generation, so that we can. And one of the nice things that will give us is we won't have to worry about operations randomly creating probes that crash Thor by connecting to it. We'll have rejected them. So.
But the counterpart is that now that you auto-scale, and the dynamic auto-scaling can also take into account that and can add the correct rules when it scales, which is something that is almost impossible to do if you are doing this manually in your own environment, right? Or at least impossible to do right every time.
It's certainly much easier in this environment, partly because of the containerization, because the rules are now at the process level. The process level is the same as the pod level, is the same as the IP tables level, if you like, where if you're trying to do that on bare metal, where you've got to work out, okay, well, there's 10 different processes running on this node, which ones are allowed to talk? It becomes a lot more complex.
Yeah, and even then, unfortunately, there is so much, you have a limit to how discriminative you can be with IP tables when you're trying to bind the process. Sometimes you just need to be general and say, okay, anything coming to this node, unless you have processes that listen to different IPs, and yet you can't enforce it. So it's I think moving to the Kubernetes approach, it's helping us quite a bit on that area. And again, it can automate things, so it's less likely the human will make a mistake as they need to reconfigure something. So that's good. Okay, great, Richard. This was a great conversation. I really enjoyed it. I think this is a great closing for this series on our journey to the cloud. And we'll be having a lot more content down the road. Thank you very much. Thank you, Richard.
Okay.
Thank you.